Okay, let's restart. So, next problem is the coolest of all that we see. So, a tree-coloring of a graph is a way in which you can color each node. Question. Oh, sorry. A tree-coloring of a graph is a way to color the nodes of the graph with three colors: red, green, and blue, such that no adjacent nodes have the same color. So, for example, this thing here is a tree coloring. This thing is not, because there is two adjacent nodes with the same color blue. Okay. And the three-color problem is, I give you a graph, and you want to know if you can three-color the graph. Problem is very important. A recreational application is, if you have the atlas, of the United States, you can see that like each state has a different color, right? Because you want to distinguish the boundaries. So, how many colors do you need to color the United States, distinguishing the states? Okay, can you do it with 3? Okay, so. Okay, is this in three-color? Who can answer? Yeah.
I think yes. If you do the two corners that aren't connected by the diagonal in the same color, and then the other two corners in two other colors, then you will get three-coloring.
Exactly. Thank you. So I can make these two red, and this one green and this one blue, and I get a three-color. Is this one in three-color? No, because it's a 4-click. Right? Yeah. So no matter how you put 3 colors, 2 nodes will have the same color by the pigeonhole principle. Those 2 nodes will be connected. Okay. The question is, I give you a graph, is it three-colorable? So again, this thing is believed to be hard. And there is an amusing story. I think someone a few lectures ago said, 2 sat is easy, 3 sat is hard, and what about 4 sat, and so on. Right? Maybe it was you who asked that. So this is a good example in which you can actually exhibit that. So for this thing, this small digression, we have to consider graphs which are planar, so like these ones, which you can draw on the plane without intersections. Okay, it's like maps. Okay, so to coloring a map is easy. It's always easy to color. So to know if it's too colorable, okay? Because start anywhere, put black, then all the neighbors have to be white, and all the neighbors of those guys have to be black, and so on. So it's straightforward. You can do it in linear time in the input. 3-color, even for maps, even if it's planar, we're going to show for general graphs, but very similar argument, even for planar graphs, is hard. And then 4-color, there is an amazing result, which is called the 4-color theorem, that says that it's super easy, because the answer is always yes. So every map can be 4-colored. Strange, but this is how complex it is. So 2-color is easy, but it's not completely trivial. Like you have to follow these kind of like paths. So black, white, and then if you don't cycle back, then you can do it. So there is something to check. 3-color is hard, and 4-color is trivial. It's always yes. The answer. You can always 4-color map. So it's kind of amusing. So we're going to see a piece of that by seeing that 3-color for graphs. So we're not going to worry about intersections now. Is hard. Okay, and to make it happen also for planar graphs, it's a gadget which kind of like if you have intersection, you just make a very messy graph which gets rid of the intersection, which rewrites this in a planar way to keep the coloring. It's not particularly hard. Like once you know that's what you want, but we will not see that. Okay. So same structure as before. We're going to give a reduction R that given a formula outputs a graph. G phi that's recoverable if and only if the formula is satisfiable. Okay, and that's enough to prove the theorem. Okay, let's do it. So here is how the thing is going to look like. There are three special nodes in the graph, which are called the palette, like the painter's palette, and which we name as follows. So one of them is called false, F, one of them is called true, and one of them is called B, for base. Okay, we will see in a second why the thing is useful. Okay, then for each variable, you're going to put two literals, X and not X, and you're going to connect them with an edge. And for each clause, you're going to put 6 nodes in the fashion over there. Okay, these two triangles connected. Okay, so for each variable, you have an edge. For each clause, you have these six nodes, and then I'm going to tell you how you're going to connect all these things together. Okay, and then we'll see a picture. Okay, so for each variable, you're going to connect its edge, X and not X, to B. Okay, and for each clause, you do this gadget here. Okay, so this is the 6 nodes for the clause. You connect them to this palette in this way. All these ones are connected to the same palette. And then you stick at the bottom the literals in the clause. Okay, these 3 bottom edges will be connected to the literals in the clause. Okay, so as you can see, it's pretty fancy. Let's see a picture to make it more visual on how this thing works. Okay, here's a formula with just 2 clauses. And here's how the graph looks like, okay, to give you a concrete idea. Okay, so there is the palette. A question?
So are you reducing 3-sat to tricoloring now?
Yeah.
Or are they, okay. I thought you were going the other way.
No, actually no, we're always, these 3 are always in the same direction. So given a formula, I'm gonna construct a graph. So there's only one palette, it is up there. Then every variable has its edge over here. Each clause has this gadget of 6 things. So this gadget here is for this first clause. This gadget there is for the second clause. And right, you connect these gadgets to the palette as shown before. So this node here goes to B and goes to F, for example, and so on. The most interesting thing is that right, these bottom nodes here will correspond to the variables. So this clause has X, Y, Z, so this goes to X, the second one goes to Y, this third one goes to Z. Okay? Second clause here, there is a not X, so you connect to not X, not Y, and Z, right? And so on. And they claim that this thing is tricolorable if and only if the formula is satisfiable. So let's see how that works. Okay, so first let's make some remarks. So we want to prove that phi is intrisat if and only if G phi is tricolorable. Let's make some remarks about what the structure of the graph tells us about the possible tricolorings. And we're also going to prove a fact that's going to be useful. Okay, so the color of this guy, the true node. Remember, the nodes can be colored arbitrarily. So this palette are 3 nodes which are all different colors, so I just give them names. T is the color that represents true. Okay, so if something is going to be colored like T, is true, so you're going to think of T as being green. F is false, and B is something else which is not true or false. And remember that you connect like this. So I claim that if you have a tree coloring, all the variables have to be colored either true or false. Okay? That's obvious because the variable is connected to B and also to the negation. Okay, because you connect to B. And of course, X and not X must have different colors because X and not X are connected. So either you make X green and not X red, or you make X red and not X green. Okay? In every tree coloring, this is always the case. If there is a tree coloring, it makes X green and not X red, or X red and not X green. These two, regardless of anything else. Okay? So you can think now, of a tree coloring, how to map it to an assignment. Right? If you have tree coloring, you can think of true, false for the variables, depending on whether X gets green or red. Make sense? Okay, and now let's see why this strange graph is useful. What's the idea behind this? Well, the fact that we claim is this. This graph below is tree-colorable if and only if either A or B or C are colored true. Okay, and that's the whole point. So this gadget mimics the truth of a clause, of a single clause. So let's prove this fact. Okay, let's suppose by contradiction that A, B, C are all colored F. Okay? Or red. Then what would be the color of P? Who can tell us, except the people who always talk? What would be the color of P? Yeah. What's that?
It has to be green or brown, right? That's way true or false.
Can it be true? Can it be green? Well, if P is green, then what color can this guy be? What color can this guy be? So can P be green? No. So what color is P?
Brown.
Red, right, or brown, yeah. P is red. Okay, so now we are back at the same argument, right? There is this gadget of 3. P is red, C is red. What color as Q should be? If you don't look at the palette, it should be red. Right? Can be blue because there is connection. Can't be green, otherwise both these two guys have to be blue. So Q has to be red. But that's not possible because Q also has the connection to F. So then Q should be F, but this is not a valid 3 coloring, okay, because of this edge here. Okay, so if A, B, and C are all F, then P is colored F. And otherwise, if any of them is green, you can color it green. And basically this this triangle here is just the truth. It's like it's the OR. It's the OR of those two variables. So if A is green, you can make this thing blue, and this thing I guess green. Confused. So if A is green and B is red, this thing has to be blue. Sorry, it doesn't have to be blue. It can be red. Okay, good. So this is red, this is blue, and this thing becomes green. Okay, so think of this triangle as doing OR. It's doing OR of two things. You can make this thing green, and then you can also make Q green, and again everybody's happy. Okay, and if you don't want to think of it as an OR, you can just show that no matter how you color these three bottom things with one green, at least one green, you can always color the top green, but it's just OR. Okay. So this completes the proof that this gadget works as intended. And now it's kind of like obvious, right? I mean, once you have this thing in place, the graph is tricolorable, then all the gadgets are tricolorable, which means that all the clauses are true. And if the clauses are all true, you can tricolor every gadget. A question, yeah?
Could you explain how you drew the circuit, like why it looks the way it does? Or is that just definition?
Explain, sorry, what, this gadget?
Graph, yeah. How did you draw like the edges and the vertices, and like why did you connect them the way you did?
Right, okay, so I think a good way to think of it is that just a single triangle, this one here, implements OR of two things. Okay, so if both A and B are red, this guy must be colored red. It's like OR. If any is green, this guy will be colored green. This is in any three coloring. And then you take the OR of C and the output of the OR of AB. That's what this thing is doing.
Why did you make the F and B to the top two?
Well, this palette here is to ensure that this thing is really doing OR. So to make OR, you have to sort of like to forbid B at the top. So you connect this B at the top, here and there. And you connect this F here to make sure this just says, this top cannot be red. This means that this has to be green. So this thing is tricolorable if and only if the OR of this tree evaluates to 1, evaluates to true. So that's the idea. Any other thoughts? Okay, so let's just again go through this claim now. So phi is in trisat if and only if G phi is in tricolor. And let's just see what we say. Okay, and again, we always start. Okay, so the beginning. Okay, so the palette you can color it arbitrarily, TFB. Then you suppose that phi has a satisfying assignment. Okay, you always have to have this line, and then based on that, you have to tell me how the tricoloring looks like. Okay, so you're gonna color the literals T and F accordingly. Okay, so if X is true in the assignment, you're gonna color X true and not X false, That's okay because these two nodes don't touch T or F in the palette, and you're going to give different colors to X and not X. And then you're going to color all the nodes in each closed gadgets with effect, right? Because each clause is satisfied, then there is a way to tricolor each gadget for the clause. Okay, it's okay because each clause has some true literal. Okay. That's the forward direction, and the reverse direction is similar. So suppose that GPhi has a tricoloring. Okay. Now remember that we said in any tricoloring, either X gets green and not X gets red, or vice versa. That's the only two possibilities. So use that to define assignment. If X got green, define X to be true. Okay? So X and not X are colored T or F and non-conflict. And this gives some true literal for each clause by defect. The only way in which the tricoloring was valid for each clause gadget is that at the bottom three, one of them was green. So one of them is colored green, which means that the assignment that you define satisfies the clause. Okay. So based on the assignment, define a coloring, and based on the coloring, define the assignment. If you don't do this, red flag. Okay, and that's the whole proof. It's easy once you have this fact in place. Here's an example. Okay, formula with assignment 001, and so X is red and not X is green. Y is red, not Y is green. Z is green, not Z is red, and both clauses are correctly tricolored, and the whole graph is tricolored. We're done. Well, it remains to argue that the reduction runs in polynomial time. We're not going to say anything much different from before. You need to add the variable nodes and the edges. And for that, you have to cycle over the variables. Then you have to cycle over the clauses. Okay, to put the closed gadgets. There is one gadget per clause. So that's most of the input length. So the overall actually is just linear here. It's just linear in the input length. That's for us, and that's for us is the conclusion. Okay, so recap. We saw many polynomial time reductions, and the ones that we saw were from trisat to click, subset sum, and tricolor. These problems look somewhat different, but nevertheless, any of them solved fast will allow you to solve fast trisat. And what about other connections? What about, if you can solve fast trisat, can you also solve fast the other ones? And we will see later that the answer is yes, but we're not going to prove it the reductions. We're going to prove a very strong theorem which does everything in one shot, basically. But I can tell you now the answer is yes. All these problems are equivalent. Okay, and there are many, many other polynomial time reductions. They form a fascinating web. I mean, you can literally take a wall and fill it with problems that people have considered in various fields like engineering, chemistry, math, economics, optimize a portfolio, find this, that they're all connected with these reductions. And coming up with reduction is not a mechanical procedure, is art. And the best demonstration of that is this picture.